Sanjib Sabhapandit's talk on non-equilibrium system and stochastic processes.
So hopefully by the end of the talk, these words will become clear and nonlinear will become non-equilibrium and this thing. Yeah. So okay. So I think it's a very good idea that this time, we have come together this forum, and I think we should have it maybe every 2 years at least, or 3 years. I think this is we keep having these in-house meetings, but I think this 15 minutes is not, good enough for this thing. Okay, so let me start with, so this is, okay, it's very general title, but as I go along, it will become a little bit more specific. But this is the general theme I basically work on, and the idea is to give an overview of the theme and also highlight some of the works I have been doing, and probably I'll just talk about something a bit more towards the end. So before I go to the work, so okay, I have been fortunate enough to actually work with many brilliant people, including students, some experimentalists, in-house experimentalists here, and so many of these collaborations actually happened just meeting them, apart from the students, of course, and these in-house people, that probably happened over coffee, started from coffee. So many of these collaborations happen just going to a conference and just talking to people, like that, and it started. And RRI has been very supportive of this visit so far. So suddenly, that's why, okay, you see that why I get upset when, because of these new restrictions on this travel. So I feel as if like somebody just cut my wings. So I'm allowed to walk or maybe jump a little bit, but I cannot fly. So I hope that, although the director is not there, hopefully the message will go to him. I hope the director will do something about it, because otherwise we'll end up killing science after 75 glorious years. Okay. So with this very grim note, let me just move to the more fun part, which is the actual work. So what I'm going to do, I'm just going to give a very brief introduction to non-equilibrium systems, because we are here, people are from various different fields, and I'm sure most of the people here, they know what non-equilibrium system is, but let me just give you a more formal definition, and then I'll give a overview of my research interest and highlighting once in a while some of the works, so I'll not be able to highlight all. And that is the reason also I put actually all my collaborators in the beginning. So I'll not be acknowledging anybody during the talk, because I'll not be able to acknowledge everybody, because I'll be just picking up few works. So I thought that it's probably better I'll just acknowledge everybody at the beginning. And then I'll focus on the bit more on the recent activities, and then just to conclude. Okay. So, so we all know what is equilibrium. We have all studied in our MSc or even before that. So let me just start with an example to just remind you what is equilibrium is. Suppose you have a box of gas. It can be this room, just close the thing. It can be either closed or it can be in contact with some thermal reservoir at a fixed temperature. So let's assume that it's contact with some fixed temperature. You can keep the fixed number of particles fixed, or you can also contact with a particle reservoir where you allow particle to go in and out of the thing, but you just keep a fixed chemical potential. Or you can impose various other conditions, like you can keep it as a fixed pressure instead of a fixed volume, or so on. So we define. So the statistical mechanics is basically a way to describe macroscopic properties starting from some microscopic. Okay, so this is a, in some sense, framework, or you can call it a recipe. So what you need a configuration, okay, to define the system. So for example, if it is a, let's say, gas, so this configuration is basically given by the point in the phase space, and this phase space is basically phase space of the whole system. So it's large dimensional space, and each set of given set of positions and their corresponding momentum, that defines a one single point in the phase space. Okay, so that defines my configuration. So you also need to define an energy of the system, and in this case, this energy is just the kinetic energy of full system plus the potential energy. And I'm not specifying any form of the potential energy, so it will have some form. So what is the framework of statistical mechanics say is that, so given a configuration, so the probability of that configuration is a priori given to you. You do not have to compute this probability, and this probability is given by this one. So this is in one particular ensemble, but you can go to a different ensemble, it would have a similar probability, but this probability is given to you. Okay. And given this probability, you can compute all macroscopic properties of the system in the equilibrium system. Like for example, if you want to compute pressure or heat capacity, anything. Okay. So this is this configuration here. This configuration need not be the actual microscopic configuration. For example, if I look at a magnetic system, so we will all know that magnetism is a quantum property, right? We cannot get magnetism in classical system. It's a inherently quantum property, right? But what happens if I inside a magnet? So at the atomic level or whatever molecular level, this magnetization arises from quantum mechanics. But then certain systems where basically where you have this completely unfilled this thing. So you have magnetization and they try to align. Okay. But this aligning interaction is a short range interaction. So what happens? They basically form this kind of domains. So within a domain, so this is basically a schematic picture. So you think that this is just you can just think of it as like a small magnet, and they point in one direction. And if you go to a neighboring domain, it will point to some other direction. Okay. So at this level, so now you can treat this as a classical system. So you basically it's a collection of these magnets, right? So you cannot forget about quantum mechanics, although it came from quantum mechanics. So we have now collection of these small magnets, and this configuration of the system is basically defining the direction of the arrow and maybe the value of the arrow also, magnitude of the arrow also. So that defines to the configuration, right? For example, this is one configuration, and there is an energy for the system. Now, what is this energy? So this energy is nothing to do with now your quantum Hamiltonian, right? So this energy is something which says that basically what kind of interaction you have in the system. Okay, so you can actually, it turns out that it need not be a very unique. So it all says that okay, what kind of property or symmetry the system has. It says that okay, these arrows they like to point along the same direction if it is a ferromagnetic system. So you can even write down a Hamiltonian as simple as Si dot Sj, where Si and Sj are two arrows, and with a minus sign saying that when they are pointing in the same direction, this is a negative, so it reduces the energy, and sum over all I and j. Yeah.
Is given in terms of the interaction energy. Of course, there is a kinetic energy part, so this you are mapping somehow.
So there is no kinetic energy now in this system because this system is like a frozen. You can just think of it like a use this arrow and they just move. They don't. There is no motion. Unlike.
Are you assuming t equal to 0 kind
No,
of?
it's not t equal to 0. So imagine that you have a magnetic system and all these domains, so they point in one direction. There's no movement of this domains are they are not going and colliding with each other.
But there should still be some
That's
fluctuation.
That's in the your whatever the atomic level.
I see.
Right.
Okay.
So at this stage, you basically, if you look at it under a microscope, that is this is what you see. This is about 20 micron, and what you see is that these domains.
So the
right?
fluctuations are at the atomic level,
Yeah.
and that you are ignoring.
Yeah, so that I'm not writing down that atomic Hamiltonian. So if you write down that atomic Hamiltonian, of course you will put a kinetic energy. So this is the effective Hamiltonian. So this Hamiltonian has nothing to do with your quantum mechanics Hamiltonian, right? So this is not even your classical Hamiltonian. It's not even the Hamiltonian you write down in classical mechanics, right? But given this configuration and given this energy, so you can now write down the probabilities of each configuration because you will have different configuration depending on which direction these arrows are moving, right? And given this thing, your description of whatever equilibrium system is given in the sense that given this, you can compute anything. It's a question of now mathematical question whether okay you can compute some integral or some or not. It's just a mathematics now. Whether you can do that mathematics or not, that's a different question, right? But you know what to do. There's no confusion. Okay. So this is what equilibrium is. So now, what is non-equilibrium? Non-equilibrium is basically what is whatever is not in equilibrium, right? So you can have a system, for example, which is not in the environment it is supposed to be, right? For example, you have a hot cup of coffee or some cold beverages. So you have taken out from that environment and put it somewhere, let's say in the room temperature. So that system cannot be in the equilibrium with that environment. So this is a system which is moving towards the equilibrium, new equilibrium. So given enough time, this hot cup of coffee or whatever this thing is, they will move to the equilibrium, it will go to newer. So these are the system, it's going towards equilibrium. So these are transiently out of equilibrium, these systems. You can also take a system, maybe take a iron bar. So if you keep it in the table, it's an equilibrium system for long enough. But if you, one side you put one temperature, other side you put another temperature, this system is not going to be in equilibrium, irrespective of, it doesn't matter how long you wait, because you have put two different conditions on both sides, right? So what will happen in this system will reach a steady state. The state of the system will be time independent after some time. That time independent state will be a non-equilibrium steady state. It's not a, that the measure of the state will not be given by this exponential of minus beta times a. So that's a different measure for that state. Okay. Also you can have a, so this is a basically system which is out of equilibrium moving towards equilibrium. This is a system which could have been in equilibrium under proper conditions, but you have kept it out of equilibrium permanently, okay, as long as you maintain this thing. But there are also systems which can be non-equilibrium inherently because of its dynamics, right? For example, if you go to Pramod's lab, he will show you under this microscope that you have these bacteria and they move around like that. So if you look at this system, their dynamics is a non-equilibrium dynamic. It's an inherently non-equilibrium system. Okay. So I am going to
Gas in the box.
I am going to come to that.
I mean, why would
Yeah.
this be?
I'm going to come to that actually.
Previous example, that equilibrium system where you replaced, like you considered macroscopic domain. So now I was wondering that regarding this fluctuation, that some fluctuation should be there, right? For example, if you otherwise hold it, then given long enough time, it should sample different configuration.
Yes.
So
But what are those configurations? So what you are thinking, I mean, you're right. Let's see. Actually, what happened is that these domain wall moves, they become bigger.
Exactly, yes.
But instead of thinking this domain wall moves, you can discretize this. So the idea is that basically you look for the minimal model. And the idea of looking for the minimal model is you are looking for universal properties. And the thing is that the universal properties do not depend on the exact microscopic. Now, either you think that, okay, his domain wall slowly moves, or just think that these domain walls are just a square grid, forget about this thing. And the whole domain wall suddenly flip. So now whether this domain wall slowly going to the other side or that side domain suddenly flips, that doesn't matter.
yes.
In the universal properties.
Right.
For example, if you look at the, okay, that will change at what temperature, for example, if you change the temperature, this state will go from this ferromagnetic to paramagnetic. The temperature will depend on your exact modeling. But at that temperature, how the magnetization increases as a function of temperature, that property will remain same. Either you call that this domain will move slowly or just the neighboring domain will flips, basically, right?
But I mean, the
And the
even
flux-
in the unmagnetized one, for example, so there is some slow or fast evolution should go
So
on.
I am not talking about anything evolution. You do not need any evolution to describe statistical mechanics.
No,
There is
evolution, I mean that if you just take one arrow and you look at after, let's say,
There's
one
no
day.
time. So far, I am not talking about time. I am coming to time. So far, there is no time. You take different snapshots.
Yes, yes.
Okay, there is no time in equilibrium statistical mechanics. There is no time. Okay, so I'm going to come to the time in the second transparency. Okay, so far there is no time. So I'm not going to tell you how these arrows are flipping from one to another. This is one configuration. Next configuration we take some other one, and that probability of that configuration will be given by
Yes.
just this one.
Right.
And this gives me everything. I'm not telling how this configuration goes from one configuration to another. I do not need to tell you. If you want to compute magnetic susceptibility, for example, or magnetization, you do not need to know how this system going from one configuration to the another configuration, right? So I'll come to the dynamics, right? Yeah.
That equation, I mean, it says that we have states at different energies. So, which configuration? Why is one of those configurations more energetic compared to another configuration?
Because you take just two spin, two magnet. If you take two magnet parallel, they are
Oh,
less
you are-
energetic to the. Because these are just two things, no? If
Okay.
two magnets are aligning this one, that will reduce energy compared to if you are anti-parallel.
Just the alignment of the spins.
Yeah, exactly. Or in this case, you can just look at the total energy of the system, and I mean it will have different energies. Yeah. Okay. This one, no. Okay, just yeah.
Sanjib. Okay.
Which one?
With time. Suppose you,
This one.
yeah, keep, not fire, suppose you
This
keep
one.
it.
This one will come to
Yeah, yeah, yeah,
equilibrium.
the fire one.
It will not come to equilibrium because you will always keep the fire and you always keep the ice.
You'll have a steady state.
You're thinking that the ice will melt. No, you will keep replacing that ice.
Suppose you put this at plus T, this at minus T, but
Yeah,
finally it will come to equilibrium.
it's a steady state. So there is a difference between equilibrium and a steady state. It will come to a state which is time independent.
Okay.
The time independent state, the measure of the probability of the state is not given by this one. So this is equilibrium. Equilibrium is a very specific kind of time independent state. Okay? Time independent doesn't mean equilibrium. Time independent means steady state, stationary states where properties do not evolve in time. Right?
And equilibrium means?
Equilibrium means the probabilities of this state is given by that. And it will become more clear in the next transparency what equilibrium means basically. Yeah.
I'll just quickly, it's not a philosophical question or anything. That, no, that bacteria, what is going on there, I couldn't see. That your bacterial Pramod's picture.
Pramod's picture.
I just saw black with
is
some
all-
white spots.
All these Pramod's babies, they are moving around basically like.
Maybe from this,
No, there's this small thing. You can see there's all this thing. They're just
maybe
going
from
around.
this angle I can't see very much.
So there are this small bacteria. They're just going around.
Yeah.
Huh? So that is why I'm saying this is a non-equilibrium system.
Because it's always moving.
Right? This is a non-equilibrium system. Right? So this system is inherently non-equilibrium because of its dynamics. Right? Okay. So now, you had something here.
So you parameterize the equilibrium, non-equilibrium in the previous slide through that equation via temperature. And most of your examples are based on temperature. But one can think of situations where even temperature can be uniform, but still you have a non-equilibrium. Let's say you may have some.
So that's what I'm going to come. What is non-equilibrium? The next transparency I'm just going to come. What is non-equilibrium?
But in that case, how will you write that
I'm
equation?
going to come. That's the next one. Okay. So now, as I say that anything you have to describe on this transparency, right? You need a dynamics. Without dynamics, you cannot describe on this transparency. Even this one, the thing which is out of equilibrium, going towards equilibrium, it's evolving in time. So you need to describe, introduce a dynamics. Okay. So what is this dynamics? So let's first talk about it. Equilibrium dynamics.
Does the notion equilibrium, non-equilibrium, it depends on what you consider as your macroscopic variables, right, or not. And for example, if I took 10 to the 23 bacteria in a, and put some temperature, etc. over there, and I looked at some, I don't know, macroscopic things, would that not correspond to?
I'll come to that
an
at the end of the
similar to Sumati's
Yeah.
question.
I'll come to that at the end of the
Okay.
talk. This is I'm going to actually spend quite some time on that part towards the end of the talk. Actually. I'll come. Yeah, I'll come to that actually towards the end of the talk, and I'll spend some time there actually. So now equilibrium dynamics. So as I said that if you want to describe a system in equilibrium, any equilibrium properties, magnetization, susceptibility, specific heat, pressure, you do not need a dynamics. You need various copies of the system, and these probabilities of these various copies are given to you. Right? You can compute anything. But any time dependent properties, for example, how does the system approach to equilibrium? You perturb it from equilibrium, how does it come to equilibrium? Or you are keeping a system out of equilibrium, right? Like this two things, fire and ice. To describe this, you need writing. Or even compute two-time properties like somebody asked, you asked, I think Sainton asked. Even in equilibrium, if you want to ask two-time properties, you need a dynamics. Or even to perform numerical simulation, right? You want to study equilibrium system in a computer. So you need to perform a numerical simulation. You need a dynamics. Okay, so you need to introduce a dynamics. And this dynamics has nothing to do with the dynamics of the original system. Like for example, if you take a gas, you know that the dynamics is Hamiltonian dynamics. They follow Newton's law if it is a classical system. Or this magnet, maybe just the quantum Schrodinger equation or whatever this thing. So this dynamics is nothing to do with that dynamics. This is a dynamics. It's a stochastic dynamics you introduce by hand. Okay. So it says basically you describe a probability, or it's a probability per unit time. How does the system go from one configuration to another configuration? This is basically a probability. So you have this how does the system goes from one configuration to another configuration? So this is a dynamics you introduce. Okay. So for example, this dynamics when you do a Monte Carlo simulation. So this dynamics is for example Metropolis algorithm, where it says that you are in a configuration, choose a new configuration by some local moves. Look at the energy of that configuration. If the energy of the final configuration is lower than your initial configuration, you accept it probability 1. And if it is higher than your initial configuration, you accept it probability exponential of minus beta times the energy difference. Right? So this is one dynamics. Right? Or in case of Brownian particle, like you have a Brownian particle in water. So that's the dynamics of that particle, because it's also, although coming from all this water molecule hitting this particle, you write down an effective dynamics for the. So these are stochastic dynamics you introduce based on some knowledge you have of the system. This dynamics is not unique.
In the other case, in the case of Monte Carlo simulations, you're basically trying to sample the partition function, right?
But
so there is no in that case, I agree. There's no intrinsic dynamics. But for Brownian motion, there is an intrinsic dynamics.
It's the same, because in the Brownian motion, the configuration space is a continuum. X position is the configuration space, and in this case, the configuration space is a discrete set of space. It's a dynamics in the configuration space. Whatever the position of the Brownian particle, just think of it, that's the configuration of the system. And that configuration evolves continuously. So that's a continuous configuration space, just like this gas of particle. Right?
I'm saying that one is physical and the other is a sampling dynamics.
Yeah, but other is also physical, in the sense that it is coming from something what Sainton has said, right? There's something actually going on.
Be, right? May or may not be like that.
Like
right? If I write down a partition function,
it will not be there.
It is not like you're moving from one.
No, it will not be there in the partition function, because that's a static thing. Yeah. But there is something evolving in the system, right? I am putting it by hand. So the reason that, because it does not matter what dynamics you put it, it only depends on few quantities, like what is the time scale like system spans in one configuration, and then it goes to the next configuration. There might be something internally.
So even for Brownian motion, you said that you can do whatever stochastic theory you want?
So you can do whatever stochastic theory you want, but it's not completely unique, but it's not completely arbitrary. Under right condition, it should lead you to equilibrium, right? And that lead to equilibrium, what it means that if the system is in equilibrium, if you are in some configuration C, with some probability you go from C to C prime, this is like a probability current going from C to C prime. That has to be equal to, if you are in the configuration C prime, you are coming back from C prime to C. So therefore, there is no probability current between two configurations, and this is something called the detailed balance condition. So as long as you satisfy detailed balance condition, you can put any dynamics if you are only interested in your equilibrium properties. Like for example, your metropolis rule, I can put a different metropolis rule, need not be that one, I can use a different one, right? Yeah. Yeah, exactly, right?
Yeah. Sanjib, so just my confusion was that in equilibrium you does not need a dynamics because you describe everything by probability, but that doesn't mean that system doesn't have dynamics, right? Because if you calculate some average, the time and ensemble average should be same.
Yeah, exactly. So that is the hypothesis
Huh.
of the statistical mechanics. Is said that basically if whatever your time average is same as the ensemble average, so therefore you do not need to compute the time average. So you look at the ensemble average. So what you need is that these copies of this ensemble.
Yes.
Right?
Yeah.
And that's the
Yeah. So the other way, like that, what you get from ensemble averaging, if you do a very long time average, you will get the same value.
You
so,
should get the same.
So that means the system is visiting all the different states. So that.
So in fact, if you keep it a fixed energy, not temperature energy, fixed ensemble, it spends equal time in all states. That also state includes, if I am in this room, imagine that all the windows are closed and all the gas particles are just coming to my side. That's one configuration where half of the room is empty, all air is on my side. That configuration has equal probability to any other configuration, right? So it visits all configurations with equal probability. That is an assumption, and that is a, I mean, that will take another 1 hour if I want to go there basically. Right? Huh? Yes. You can compute the probability of that actually, and it's not very different. It's just half to the power the. It's just the probability that all the gas is half side of this is half to the power the number of whatever it is. Yeah, half to the power 10 to the power 23. Right? Yeah. Okay. So now, so as long as you, so this whatever W you choose, so you need to satisfy this condition. This is called a detailed balance. So this detailed balance condition ensures that the system will reach equilibrium. So now, what is a non-equilibrium dynamics? Okay. So let me just say that detailed balance leads to equilibrium. So this W I have chosen somehow. Okay. So this is a condition of detailed balance. But okay, this is a bit difficult because you said, okay, I need to first put a potential and then look at the dynamics, find out the equilibrium distribution and find out this one. Okay. Or I need to look at the emitter. So there is a yeah, exactly. So that is why. But that thing is that this. So that is why I'm just pointing a second one. See, it almost looks like that. Okay, this P equilibrium, see, they are independent of W, but this P equilibrium actually coming from these W's, right? So another condition is the same condition. Another way of looking at only in terms of this W's is that. So you have these configurations, and let's say you have m number of total configuration, and out of m you take n configuration and all possible n. For any n configuration, you form a loop. C1 go to C2, C2 go to this thing, and then finally you come back to C1. And you look at the probabilities of that loop. So this is basically W, C1 goes to C2, C2 goes to C3, and so on. You take the same configuration in the reverse order. So now C1 goes to Cn, Cn goes to Cn minus 1. If these two probabilities are equal, okay, so that means this probability is for any set of these Cn's out of the all possible configurations, so then the system will have detailed balance. Okay. So this will ensure that this P equilibrium C is basically given by exponential of minus beta H. Yeah. Exactly. Yeah.
The equilibrium here of C would be, if it was in a Gibbs state or something, it would be e to the
It is in the Gibbs state.
it is, okay.
Always, yeah.
Always,
Yeah.
because its equilibrium
It is,
in
yeah.
that Gibbs state.
Exactly.
So that's, yeah.
It is equivalent to this. So P equilibrium C is exponential of minus beta times U of C.
So what you're saying here is that if you can rewrite that whole, you can rewrite the whole detail balancing in terms of just
the rate.
uh,
Jump
transition
rate.
from
Yeah,
it.
exactly. Yeah. So this is basically necessary and sufficient. This is basically equivalent to this one. Okay. So now you see that to reach equilibrium, you need a very specific condition. Yeah, both ways. Yeah. Okay. So therefore, you see that this is you need a very specific condition for your dynamics to be in equilibrium. So therefore, any dynamics which violates this are non-equilibrium dynamics. Right? So any stochastic dynamics which violates this detailed balance condition is a non-equilibrium dynamics. Right? So it says that basically you can just think of like all possible set of stochastic dynamics, and there is a very tiny subset of dynamics which lead you to equilibrium, which satisfies this detailed balance condition, and all other dynamics are non-equilibrium dynamics. And that is the reason these non-equilibrium systems are ubiquitous, right?
Sanjib, again,
Yeah.
when you say lead to equilibrium, so this W is a function of, it's a number.
Number.
Give me two configurations.
Yeah,
Is there time involved in that?
No. Oh yeah. No,
There is
W
time.
doesn't have time,
Okay.
but the system will evolve by some kind of stochastic equation. So you can, given this, how the system goes from one configuration to another configuration, so you can write down how the probabilities of the configuration evolve with time. Right? Because I tell you how system goes from C to C prime, right? For all set of C prime. So I start with something, so I know what are the probabilities of the next configuration at the next time.
It's a sampling process. It's not a necessarily dynamic.
So you can write down given this. So this is like the stochastic equation, and correspond to that you can write down a Fokker-Planck equation or master equation in this case what we call. So it will tell how P of Ct. So now I can write down an equation for P of Ct for all possible C, how this evolves as a function of time. So this will be some Ct, some M is some matrix, okay, given. And this if we evolve, so P of Ct will go to P equilibrium of C as t goes to infinity.
And so what are the W's? Maybe it was on the previous
W's are
transcript.
basically the element matrix elements here. What is the, how does the system go from one configuration to another configuration, right? So all it says that this matrix, finally whatever you write down, the largest eigenvalue is 0, right? So always you have a state which is time independent state. That eigen function correspond to that 0th eigenvalue. That is your equilibrium state basically in this case.
Oh, okay. Thank you.
Right?
Thank you.
And if you look at the larger or smaller depending on which direction you are, so those will give you the relaxation to the equilibrium.
So when you write down that condition, what it says is that finally your system, if your W's, that matrix is like this, then the system will finally reach equilibrium. According to this equation, it will finally go to equilibrium.
There is a condition on the matrix, and this is basically this one. Yeah. It says even the first definition says no net current in the current, but basically it says any loop you look at in the configuration space, this way probability is same as this way probability. This is also in some way saying that I didn't want to say it, but basically there is no entropy production in the system. But I mean entropy is defined by you take the ratio and then take the log of it. But okay, that let me not take. Okay. So now you see that.
Sanjib, just one.
Yeah.
So the collection of bacteria that you have shown in the earlier, so that actually meets the detailed balance.
No.
It doesn't?
No, that I will come. I'll come to that model more this thing and why it doesn't specify satisfy detail balance. Okay, so basically saying that okay, this is a state now saying that so given this, see that this the scope of non-equilibrium statistical physics is enormous. It's not only restricted to physical system where there is a temperature, right? Because you don't have to have a temperature. Okay, it doesn't have to have a physical system. Biology, ecology, finance, anything where you have a stochastic process. So it's basically a stochastic process where the process doesn't satisfy detailed balance, a non-equilibrium system, basically. Right?
The fact that because I could think of writing down an equation in which m depends on t also.
You can.
The fact that m doesn't depend on t.
It doesn't. No, that's not enough.
What physical property is it that m? I mean, because you're focusing on situations where m doesn't depend on t,
Yeah,
right?
yeah.
So what does that correspond to physically? Is that an
mean,
assumption
like,
about the kind? Because you said this is wide ranging, you know, any system like finance, etc., etc. But then all of them have to have this m which is independent of t.
Yeah,
Right?
so that's the most simple thing.
Is it just simplicity, or does it say something about some physical?
So for equilibrium, that is a simplicity. For non-equilibrium, there are even cases you may not be able to write down that equation at all. Right? This is a very big approximation. It's called a Markov approximation. Right? It says that your next state
Doesn't depend. Okay,
doesn't,
okay,
right?
It's Markovian. Okay.
But that's a very specific
Yes.
decision. But general non-equilibrium system, it doesn't necessary. This is you can do only when the system is Markovian. But even within the Markovian system, the non-equilibrium system can be anything as long as this is not satisfied.
So when you say that this is applicable to given thing like finance, then it's applicable in as much as you can ascertain that the markets don't have this Markov.
No.
The markets are
No,
Markovian.
whatever the dynamics the finance has,
Yes.
that's not an equilibrium dynamics.
Yes.
You may not be able to write down an equation for that dynamics.
Okay.
But that's a non-equilibrium system.
Yes. Okay.
Right? So that is what I am saying. In some cases, under some approximation, you might be able to write down a dynamics, or you might be able to use Markovian approximation. And in many cases, you may not be able to write down because the price today might depend on what is the price like 10 days back, right? And you may not be able to write down a Markovian equation. Right? It's a non-equilibrium. But non-equilibrium doesn't mean that you can always describe in terms of this. So what I'm saying, the equilibrium is a very specific condition, and if you break that condition, everything is non-equilibrium basically. Right? Yeah. So I am generally interested in this non-equilibrium systems, and as you said, the non-equilibrium systems and stochastic processes, they are basically the same, right? If you look at it in this way. And so what I'm going to do, okay, I'll going to focus on few specific things. See, as I said, that I'm generally interested in non-equilibrium system, and then when I look at a problem, usually, okay, you don't think of, okay, what will be the color of the basket once the paper is published. I'm going to put it in a red basket or green basket. You just study the problem, and then, okay, you find interesting. So nevertheless, I try to make some colorful baskets and try to put these problems in different baskets. But this putting in different baskets, these are not precise actually. One can look at it in a different way, or you can put everything in one basket, or one can keep moving this thing. Okay? So these are the few things I have been looking on this. So I'll going to spend very little time on this one. I'll just go through it slowly, and then I'm going to spend some time on this one, which is something I have been doing now, and I think that's going to answer many of the questions. I think Madhavan, Sumati, Reggie, many of these things. Okay. So let me first go to this question, this stochastic thermodynamics. Okay. When you say stochastic thermodynamics, it sounds a bit this thing, but there is nothing fancy about it. So it says that, so we know what is thermodynamics. You define energy, work, etc. And like today, Madhavan talked about, like you have this first law of thermodynamics, second law of thermodynamics. So we know how to define it. So it turns out that even at the stochastic level, you can define this work, heat, etc. meaningfully, which when you go to the bigger system or average, that is consistent with your usual thermodynamics. But this is basically a way of looking at this work, heat, entropy, etc. at a fluctuating level. Okay, so along each trajectories of evolution, you can define it meaningfully. So therefore, it actually gives a description of these thermodynamics variables like work, heat, etc. in this for microscopic systems. Okay, so of course this average will satisfy the thermodynamics laws, and typical fluctuations you expect it to be Gaussian always, but there are these atypical fluctuations, and these are in general non-Gaussian, and people are interested in these atypical fluctuations. So what are these atypical fluctuations? Again, I will not.
Not important that C has large number of degrees of freedom. When you say microscopic.
So yeah. So why thermodynamics and one particle basically, right?
Yeah, I thought in up to now, because you're also going towards equilibrium and so on in StatMech, that these C's were encapsulating large number of degrees of freedom.
Exactly.
So is that continues to be true?
No.
No.
So now.
So you are making a slight change.
So now what we are going to do? So we are going to look at this system. For example, you can still think of it like, okay, you can just think of it like a Brownian particle. That Brownian particle is of course interacting with a large number of water molecules. That's a macroscopic system, right? But now you are looking at the microscopic part of it, not a macroscopic part of it. And I'm now looking at how the microscopic part is behaving. Of course, if this microscopic part becomes bigger and bigger, this fluctuation will become smaller and smaller, and at some point it will behave like a macroscopic system. But the point is that how much you can push this macroscopic thing towards the small systems, basically.
And this will be an element of how you treat non-equilibrium systems, which are again systems of large assemblages.
Yeah. So it's a large part, but you might be able to look at a small part of it.
Small part of it, and then you will infer things about the large.
Yeah. So, like for example, no. So, for example, so you might ask, okay, in this room again, I keep telling that, okay, all the gas will come towards my side, right? That's a very low probability. Now, if I just make the size of the room smaller and smaller, that probability becomes larger and larger, although it is small. And you want to get an estimate of this probability, for example, right? For equilibrium systems, those estimates are easy to make. Like, for example, here I say that it's just half to the power, whatever the number of particles. But those estimates becomes difficult in non-equilibrium systems. And what we want to see is that these large fluctuations, basically it says how much the system differ from typical realizations, for example. Typical realization being basically the gas of uniform density everywhere, right? So how rare are these atypical fluctuations? So we want to have a quantification of those atypical fluctuations. Yeah.
So just need to understand this discussion. So isn't it enough to just think of it as a single particle undergoing the stochastic thing, and there are many realizations of that particular process, right? So there's sort of an ensemble of these Brownian particles, but you're looking at the fluctuations from in every path, right? I mean, you're calculating fluctuations from. I mean, I guess I'm a little confused.
No, okay.
There is a fluctuation coming from the stochastic dynamics, and then there's a fluctuation coming from an ensemble of these particles.
So, like for example, I can actually look at the equilibrium of single Brownian particle. In fact, that system need not be very large. So, for example, if I look at the velocity distribution and the position distribution of single Brownian particle in a potential, that will follow equilibrium distribution, because it is interacting with a large bath, right? This is nothing different from an ideal gas, right? Because it's just a ideal gas is single particle, no? Finally, because they don't interact with each other. So instead of looking at 10 to the 23 particle, I can just single particle will also follow the equilibrium distribution, right. So, in that level, I do not need the system to be very large, but it is interacting with a bath, and that is very large, right. But now, so this is one just an example, like the kind of question basically I have been interested in. So, this is okay. So, this is a AFM cantilever, I think this is a dimension. So, what they did is basically, okay, there is a metal plate here, and there is a I think metal, and you apply a voltage between these. Now, cantilever, okay, it's a microscopic object. So, if you put it in the air, so air is like a bath, right. So, it's a given temperature. So, it equilibrates the cantilever. Now, if you put a voltage, it puts a force between the cantilever and the metal plate, right. Now, if you vary that voltage, you basically essentially vary this force. So, now externally varying this voltage, you can apply work on this cantilever. Right. So, what they have done is that they have basically put a stochastic force, stochastic voltage, that is equivalent to putting a stochastic force on the cantilever, and then you compute the work done on the cantilever by the stochastic force. So, now what we know is that, okay, if we apply a force, external force, you do work on the system, right. But in this case, there is a distribution because the fluctuation becomes important, and what you notice is that there is also the negative work. So, what it means that the system is doing work on the external force, and this negative works. So, there people are interested in understanding this negative work. These are of course very small probabilities, but how do you quantize these probabilities, right? And in fancy way, sometimes people say that these are basically the second law violating event. Okay, no need to worry. Okay, but it basically says that those are the trajectories which are not in agreement with usually your second law. This thing. Second law says that if you are applying force, you are doing work, right? But here is basically the system is doing work on you.
So you are saying that this probability distribution, if you do not apply that voltage, then that will have a symmetric Gaussian.
If you do not apply voltage, then you are not doing any work, zero, because that's you are determining by your external force times the velocity, and then you are integrating, right? Okay. But if external force is zero, you are not doing any work, right? Then you are not again. It will go to a new equilibrium state basically.
I'm just trying to understand.
Steady is like applying a potential basically, right? So it will not, you will not do work again. That is the temperature. There's a temperature. Of course, it's causing the fluctuation, and that's why it is giving you this negative work. Yeah, I didn't want to say it, but okay, there are. It will and it will not. Okay, so I mean, some regime it will do.
What does it mean by the cantilever doing work on the voltage?
So that's basically saying that. See, it's like saying that if you have a hot temperature and a cold temperature, right? Usually heat goes from the hot temperature to the cold temperature. But if it is a microscopic object, momentarily the heat can go from the cold bath to the hot bath just because of thermal fluctuations. It's similar to that.
There are some collisions which are helping you in the.
Yeah.
That is what essentially it is.
Right. So there's two stochastics. One is the particles that are there that are doing this, but there's also, you said V also has to be stochastic.
In this case, it need not be stochastic. In this
It could
case,
just be periodic
it can
or
be
something.
anything, time dependent
So that
force
was-
basically. No. In this case there, and then we actually, so this is some experiment they did, and then actually we could compute it exactly, asymptotically exactly, and I was very pleased to see that actually, okay, I did something which, I don't know, experimentalists can see whether it's a good fit or not, but I think it's a good fit. And, okay, yeah. So let me just go a bit quickly. Okay, so there apparently it's also important in this whatever gravitational wave detectors, etc. But don't ask me why. They might have just taken that system and just computed this thing. So I'm not going to say anything about it. And the point is, how do you quantify these fluctuations, this large fluctuation? And this is a way to quantify this large fluctuation. It says that basically you have some object which is a time integrator. In that case, it was the work done. And what is the probabilities of this one? And it exponentially decay. In this case, is a time. If it is a volume, it can be this thing. And this function is a convex function. So you see that it just picks up here, and so these are typical values it picks up, and any values which are atypical, they exponentially decay in your either observation time or in this case the volume. Okay, so it quantize how rare are these atypical fluctuations basically. Okay, and this is something called large deviations. This thing, and there's a large one work on there. So let me not go through this particular example. Okay, so I had actually a lot of other things. So, but maybe let me just go through quickly. So there is other system is this granular gases where it is again a basically dynamics is something non-equilibrium. And the question basically you ask is, okay, you know that if you have an elastic gas, the distribution is a Gaussian, right? It's a Boltzmann distribution. Now if you take a box of marble and shake it and keep it here, after some time the velocity is going to be 0 because they collide inelastically. But if you just keep shaking, it will look like a gas of marbles because you are putting energy from inside and they are also losing energy. And what is the velocity distribution? Okay, so there are some work earlier. It says that it is some kind of stress exponential with beta equal to 3/2. And this is a bit counterintuitive, right? It says that, okay, elastic gas is a Gaussian, and inelastic gas, which is a tail that is more than the elastic gas. So you are more likely to find higher velocity particle in an inelastic gas. That's a bit counterintuitive. And there are a lot of experiments which seems to agree with this. So we revisited this problem, and okay, I'll not go through detail. And we found that basically, okay, so what we found within our analysis that, okay, this P of V, so in most physically accessible regime, it's a Gaussian with a logarithmic correction. So it still decays slower than a equilibrium gas, or as at least like equilibrium gas or slower. Then okay, we can ask what about the experiments? This is an experiment which seems to say that it goes like exponential of V by 3/2. So we took the same data and check it with our Gaussian thing. And I don't know which one looks better. You can decide. So it all says that basically one needs to relook this system. I would say that this is better, but okay, this might be my bias. Okay. So this is what something basically one needs to relook this theory, and in this case we have to look at only from theoretical point of view, because these large fluctuations are very difficult to get in experiments because they are very small probability errors. Even simulations is very difficult to get. So it only can come through some theoretical arguments basically. Okay, so we looked at, okay, let me just go to the, maybe I'll just go through, I have not much time I guess, right? So let me just maybe just go through something here, okay? Something I have been doing currently. So this is this active particle. So you know what is a passive particle, right? You look at a polystyrene bead from Pramod's lab and look at under the microscope and you see this jittery motion. So these are called this Brownian motion. If you just plot it, it looks something like that. So it says that if you look at the displacement in a given time delta t, it goes like square root of delta t and then some random variable which is drawn from a Gaussian distribution. Okay, so this is what your Brownian motion is. And this dynamics is a equilibrium dynamics. So Brownian motion is a equilibrium dynamics. So if you put it in a potential, it will go to your Gibbs tail basically. Okay. So now there are some particles or bacteria. So although it from far away or large time scale, it looks like doing some random motion. At a small time scale, so it goes like the displacement is proportional to the time. Okay, and there is a unit vector, and that unit vector has some stochastic dynamics. Okay, so depending on what kind of bacteria or what kind of disease, and this is a non-equilibrium system. It says that if you basically if you have a arrow, you can go from here to here. You cannot come back, right? If to come back, you have to turn the arrow and come back. So that's a non-equilibrium dynamics For a Brownian particle, you can go from here to here, you can also come back from here to here in the next instant, right? But here, if your bacteria is moving like that, you can go there, it cannot come back. First, it has to turn, that's another step, that's another state, right? So, from every state to any other state, you cannot go in this case, right? So, there is no reverse, it's a non-equilibrium dynamics, and you can have various kind of bacteria. And again, the idea is to you look at the minimal model which describes the thing. And minimal model for this bacteria is that, okay, there are some bacteria which just goes in one direction, suddenly choose to change the direction and then it goes something like that. Or there are some bacteria or genus particle, they keep moving and they just keep changing the orientation as it goes on, right? Yeah. So this guy basically they just choose a direction at random. This thing can go. So this is what people have. Yeah, yeah, yeah. Yeah, but that's a different state. X theta cannot come back to theta x, right? It can go to theta plus 180. Yeah. These are no, at this point you just think of it like an ideal gas. No, they are not colliding, independent bacteria.
So, but if you take one and then you're assuming that it's in a what kind of a bath, right? I thought this bath was very important.
So now, non-equilibrium, you don't need a bath, right? It has its own dynamics. It has this flagella, it just rotates, it goes in one direction, it goes the other way, then it just changes the orientation. It's just a stochastic dynamics inherently, and you don't need a bath. Right? So bath only you need for the equilibrium dynamics. Right? Here you don't need a bath. There's no temperature. You can put a temperature if you want, because if these guys are in water, okay, the temperature might affect that. But that's a secondary effect. You don't need to put it. It's like random walk, mosquitoes. The mosquitoes going here and there. There is no bath, right? The mosquitoes goes there. And it wants to change the direction. It just changes.
So
the
you
direction.
could just study a single bacteria.
You can study a single bacteria. Yeah, yeah. So you don't need a large, thermodynamic this thing.
The particle can go one way, it can turn, come back, whichever way it can go, right? So what exactly is the difference between the two here?
Here, see, okay, let me just see. So, see, if you look at depends on at what time scale you are looking at, okay. So, if you look at a 1 micron polystyrene bead, okay, so there is of course a velocity. Each time you have a velocity because this type collision, and these velocities are drawn from Maxwell distribution. So, now at which time scale this velocity relaxes? So, that's the time scale at which the velocity relaxes for let's say 1 micron polystyrene bead. 10 to 100 nanosecond, it forgets what was its velocity, right? So, if you are sampling this thing at let's say 1 microsecond, right? So, that's you are much beyond this viscous relaxation time. There is no velocity in this case, say overdamp dynamics.
So is it okay to say that these are directionality over a longer time period?
Which one?
The active particles.
So, these have directionality over a longer time period, and it has something more actually. So, in the free case, it has some additional properties. So, in the free case, as Ranjini says, okay, these are like it has directionality over a longer time period, and you can call it like a persistence time. It's a time at which basically it just goes along one direction and then it changes direction. So, the free bacteria, if you look at for a large time, at very large time scale, it will look like something like a Brownian particle, okay, if it is in a free system. But now something else can happen.
Actually the time frames then come into the picture, right? Because we decide the time frames, isn't it?
So, there is something else. Now, moment you put a potential, right, something else will also happen. If you look at a free bacteria, if you look at a very long time scale, look at a position displacement, it will look like a diffusive particle because it doesn't matter. It's just going somewhere there, going somewhere there. So, at very long time scale, it will look like a Brownian particle with some effective diffusion coefficient. Okay. But if you put a potential, something else will also happen. Okay. And So maybe let me just so these are something they have earlier done. So you look at this bacteria. So this is this kind of motion. I assume this is run and tumble, or this is some bacteria where they genetically modify something. I think Pramod also does in his lab. So they basically go in one direction, but they slowly move. Okay, and so you can ask various questions like, for example, what is the position distribution without confinement, or what is the steady state in confinement, and that steady state. Okay, so for example, if you look at a position distribution, as I said that, or as is saying that at very long time, of course, it will look like a Gaussian. It's like a Brownian particle at very long time. But it goes through a very interesting state. So it first goes through a phase where the probability is basically picked at the boundaries, and then slowly this central peak develops, and finally it becomes a Gaussian. Okay, all this. You look at a stationary state in a confinement, right? So you know what is a stationary state for a Brownian particle. This is just given by this, just the Gibbs distribution. So now these bacteria you look at. So there are two phases for these bacteria depending on this their persistent time. So there is a phase, okay, where this persistence time is much less than the relaxation time in the your this thing. So that behaves like a passive system. This looks like a Brownian particle in a confinement. But there is also a phase where it actually very different from a Brownian motion, and there is no time here, right? So it basically depends on these relative things.
Does that mean that it basically avoids where it's coming? So the time of return is
so what happens is
larger?
that so what happens is that unlike a Brownian particle, when the Brownian particle goes, let's say it's a solid wall, it will hit and it will come back because that time stay here. The bacteria, it will go and it will stuck there till it decides to turn.
So it avoids. Basically, the time of return is going to be much larger.
Yeah, exactly. So therefore, you see this accumulation at the boundaries basically, right? And this is basically something called an active state. So okay, so we can actually look at various phase diagram. Okay. Relaxation is very different compared to Brownian particle. For example, if you have a Brownian particle, you only have one relaxation time, but here this relaxation is something unusual in this case. Okay.
Momentum decays.
So in the this one so far there is no bath. So what bath will do is basically that this thing.
Because, like you said, in the ideal gas, you collide and you bounce back. But here, because it's like a low Reynolds number condition, the momentum decays.
So bath, what will you do is that this sharp edges, it will just make it smooth basically. So bath is not very important. Bath will just change this thing little bit basically. This thing.
Provided you're neglecting the mass, the inertial effects. No?
Yeah, it is. Yeah.
So, but you're able.
I mean, like if the temperature is very high, right, which is like fluctuation is as much as the bacteria can move, then of course this will not stay, right?
But I thought the reason you can neglect the inertial effect is because there is a bath, isn't it?
Yeah. But the point is that temperature is not important. Bath only gives the viscosity; it doesn't give the temperature, right?
So exactly, to continue on that question, I was about to ask you about the viscosity. So suppose there is a bath and suppose it is viscous. So Brownian motion happening in a viscous medium would have kind of emulated the motion of the bacteria, right?
So for Brownian motion, viscosity and temperature, these are not independent quantities. So viscosity and temperature, they are related by fluctuation diffusion theorem, right? It says that gamma times the diffusion coefficient is equal to kBT times kB times the Boltzmann constant times the temperature. For this case, it will fill the viscosity, but the temperature may not have any effect on them. Temperature will be something very distinct. Temperature is negligible, right? So that's what. So you can neglect the temperature effect. Temperature, see, because even if you look at a Brownian motion, in 1 second it moves by a micrometer. It will move the bacteria by the same amount because bacteria is almost like a 1 micron or 2 micron thing. It will move by a micrometer, but the distance it travels within that 1 second is much more than 1 micrometer. So these fluctuations are small compared to its displacement. So,
so actually like the distribution that you have drawn, that is the interplay between this persistence and the size, right? So you, also for active system.
No
if
size.
you-
Size is 0 now, for example.
No, I mean the size. I mean system size basically. Your, what is
Yeah,
it?
yeah, yeah.
So now if you increase your system size, actually the active one can also look like passive one
Yeah, yeah,
if
yeah. So
if
this
the
is
persistence.
yeah, this is just the. It depends on the system size determines this relaxation time, right?
So, what regime you are studying?
Yeah, exactly. So whether your persistent time is larger in relaxation time or smaller in relaxation time. So now, okay, let me go to a slightly different kind of bacteria, and which has two time scales. Okay, so they are these bacteria where they move in one direction, like this guys, and suddenly they want to just change the direction. So they go there and this two time scale. So this also you can see it in some kind of experimental system. So depending on what color light you put, so you go in one direction and suddenly you changes the direction by 180 and then you go there. And we'll look at this kind of system and you can again model this kind of system. And here of course you still have these two. So this is what you look at, right? So this is if you just take it, these are all non-interacting particles, you just take it and just evolve it, you look something like that. And this is, you see that it immediately becomes Gaussian, isotropic. But there is a regime here, so that just comes from the interplay between these two time scale. So very basically there. So this is just the old, this is the old two regimes, and this is basically coming from this interplay between these two time scale. And in this regime, if you look at the fluctuation, this is a position fluctuation on the perpendicular direction. It has a very interesting this thing, and it turns out that you can actually calculate it exactly. So it has a ballistic scaling. So this fluctuation goes like time now, not square root of t, and you can actually compute this is exactly just a product of these two gamma function, and this is something what you can show. Okay, this is the parallel one, still Gaussian. Stationary state, again you still have these two regimes which are this passive and active, but now because of this another time scale you can have two other regimes in this case. So this is like a passive like regime where this is concentrated in the center, but this is a very interesting thing. It is concentrated, but there is a divergence at the center. And even in the active regime, the general active regime it was there, but here you still have a divergence basically. And so this divergence correspond to basically all these things basically when they have to pass, they pass to the center. I think there is this drawing thing earlier, right, which goes back and forth, and if you keep doing that, that center portion tears. That tearing is that divergence basically, right? You can actually compute the expression for the tearing, and this is what it is looks like. And you can also look at the cut in one direction, and you can find, and you see that, okay, so these are the divergence depending on whether it's passive or this thing. And you can also look at the marginal in one direction, and you see that this divergence is basically it's a logarithmic divergence, so it's still integrable, right? And now you see that this is the passive regime, so you still have this Boltzmann tail, so which is basically Gaussian, right? But accompanied by some logarithmic divergence at the distance. So coming back to your question, basically, so there is a regime where it behaves like a passive thing, but there are corrections to this, and there is of course some regime where it completely behaves like it's very different from a passive thing. But there is a regime where it behaves like a passive, but sometimes there is a important corrections. Okay, so maybe I'll just okay. So this is, I think this is something I talked during the in-house. So maybe I can just let me not talk about this. So basically, what I try to do. So it's not important that I finish everything. So the idea is to basically give an overview of what non-equilibrium system is, and I hope that's why I took quite a lot of time to actually explain, and I hope you got an idea of what is a non-equilibrium system is. And so as I said, that basically non-equilibrium system is, they are defined by dynamics as opposed to statics, which you do it in equilibrium statistical mechanics. And this dynamics can be anything depending on your system, right? So, this some stochastic dynamics which doesn't satisfy detailed balance. So, therefore, the scope is enormous. You can actually look at any system, right? So, the common threads of running across my research is basically these are the systems described by stochastic dynamics. So that is why I say that, okay, although I put these different colors, although it might look like that, okay, I am all over this thing because, okay, I am doing this, that, this thing. So these are essentially the same systems. So these are stochastic systems which doesn't obey detailed balance. And okay, these are important areas of research, and okay, there are a lot of open questions, and okay, yeah.
So we can have a quick one question, other we can discuss during tea time, tea break. So we're already late.
So you were telling us mainly about dilute systems. Now suppose you had a dense system, a metastable system like a glass. Is it fair, in your opinion, to say that this is basically a non-equilibrium system where the residence time in each state is very, very long?
I think some people also call it the equilibrium system moving towards equilibrium, I guess, right?
That's slow, is it?
Yeah, I think that's what somebody says, no? This is like a glass is not very different from it's moving very slowly, right? Instead of this one, if you put like a very thick liquid and you are basically prepared in a yeah, I wanted to also talk about something extremes, which the reason I wanted to talk about is I found it quite interesting actually. This okay, maybe let me just this one, I think, yeah. So this is something basically, okay, so what we looked at is, okay, so this is just a 1D Coulomb gas in a harmonic potential in some temperature, so it's a this thing, and you ask, okay, so 1D Coulomb gas in 1D potential basically, so these are just the linear potential in a harmonic potential, and you ask what is the fluctuation of this right side particle, this is the extreme particle. And so I'm not going to say what we did, but why is it important? Like because I think two transparencies back I was showing some apocalypse like situation, and then I just immediately after two transparencies I am just going to something very mundane, right? So why is it important? So this is important because of something called universality. So if you look at this extreme, so what are these extreme? So these are event. So we keep talking about extreme temperature, extreme heat wave, or something like that. So these are large events, and usually there is an underlying stochastic process, and you are asking basically, okay, what is the largest of this stochastic process within a given range of time, or you have a n collection of this data, and what is the largest one, right? So if you don't have anything, you start with a null model. Null model says that all your random variables are uncorrelated. So it turns out that if all your random variables are because otherwise it doesn't make any sense, right? If you want to compare with something, temperature or heat wave or whatever. So you start with a null model. It says that if your random variables are uncorrelated, then you ask, okay, if you have n random variable, n uncorrelated random variable drawn from some parent distribution, what is the distribution of the maximum of that? So that maximum, it turns out that it can be only one of the three classes. So if the parent distribution is a power law tail, so then something called the Frese class. So if the parent distribution decays faster than power law, but still it goes all the way to infinity, so that's something called Gumbel class. Or if it has a finite cutoff bounded, so then something called a Weibull class. Okay. So now, okay, imagine that, okay, your distribution is not completely independent. There is some correlation, if you take n large and if there is a finite correlation length, right, you can still think of it like some renormalization block thing that, okay, you look at this block and you look at the maximum of this block, and this maximum will be again uncorrelated and it will merge to one of these laws, right. So therefore, any weakly correlated random variable will go to this law. But there are other class where the random variables are strongly correlated. So for example, if you take a trap Brownian and take a Brownian particle, single Brownian particle you look at, and look at the position, one particle. So it will have a distribution. So you take a 10 particle, they are non-interacting. So each particle will have a position, and you look at the position and you compute the maximum position. Because they are non-interacting, it will go to one of the. Now you put a interaction between these particles. So if you put a logarithmic interaction between this Brownian particle and you look at the maximum, so it turns out that the distribution of the maximum is something called, is given by something called Tracy-Widom distribution. Okay. So this is a class which actually appears in, so it initially started like basically if you look at a random matrix and then you look at all the eigenvalues and look at the maximum eigenvalue. And so it turns out that it appears in many different cases, including distribution of the proper time in Sumoti's causal set theory. And the reason is that I think, so we should talk that basically what happens, so if you take a random graph, so you take a random graph and you ask what is the longest random graph, it would have a distribution, and that distribution is given by Tracy-Widom distribution. You take this something called this linear longest longest subsequence. So you take a look at the distribution given by Tracy-Widom. So that is a universality class, and that's because like in this path problem, all these paths are not independent. They share a lot of this common this thing. So this serves as class of very strongly correlated random variables. So in that case, basically we wanted to look at, so that class correspond to basically in this Coulomb case is basically Coulomb particle which they are logarithmically interacted. So we wanted to see, okay, if you instead of logarithm you take a real actually 1D interaction. So how does that universality class change? And so what we found that it actually gives a new universality class. We don't call it, we cannot call it universality class because we don't know any other system which follow, but it follows as something different from Tracy-Widom distribution basically, right? And okay, so it follows some eigenvalue equation, and okay, you can basically find it there. So I found it quite interesting that okay, you take a problem here and it can appear in some other field, including I think airplane boarding, as we heard. Yeah. Okay.
Okay. Let's thank the speaker.